Hello, and welcome to my presentation for the Innovative Concepts for Exploration session of the 18th International Planetary Probe Workshop on July 27, 2021. My name is Samuel Albert. I'm a PhD student at the University of Colorado Boulder in the Autonomous Vehicle Systems Laboratory. And I want to thank my co-authors, Dr. Bobby Braun and Dr. Hans-Peter Schaub. Today, I'll be presenting our work, Co-Delivery of Probe and Orbiter via Aerocapture for Interplanetary Missions. Okay, so I'll begin talking about the co-delivery concept itself, and later I'll conclude by going through a specific mission scenario that would take advantage of this co-delivery concept. So to quickly define terms, in the lower left here, I've diagrammed Aerocapture, which is the well-studied technique of flying through the upper atmosphere upon arrival to reduce the spacecraft's energy and capture it into the desired orbit. And this is beneficial because it can reduce the amount of required propellant compared to propulsive orbit insertion. So I've drawn a dashed box here around the region of initial atmospheric entry. We'll zoom in and look at the proposed co-delivery concept, which would have a probe and orbiter approach on a single trajectory and thus enter the atmosphere with nearly identical conditions, nearly identical entry velocity and entry flight path angle. They then diverge during atmospheric flight due to differences in their aerodynamics and potentially due to differences in how they apply their respective control authority. The probe follows this trajectory down on the surface. The orbiter stays higher in the atmosphere and proceeds to skip out later and follows this Aerocapture procedure. So the motivation for doing something like this is that by targeting a single entry state, approach navigation is simplified. Without this method, to co-deliver probe and orbiter would generally require either propulsion on the probe or a divert maneuver by the orbiter shortly before entry. These options are not impossible, but they do present challenges for the design of the mission, and these challenges have been relevant to a number of past mission concepts. So this proposed co-delivery method provides one alternative approach. This is really meant for either ride-along secondary missions or for delivering supporting infrastructure, such as, for example, if a relay orbiter is required for a probe that doesn't, and that orbiter does not already exist at the destination of interest. So we've mapped the feasibility of this concept across a broad trade space, and we've done so using these charts, and I'll walk through this step by step. I'll be showing the results for Mars today. We have equivalent results for Earth, Venus, Neptune, and Titan. This is all going to be for a 6 km/s planet relative entry velocity at Mars. The center chart shows ballistic trajectories, and the top and bottom charts show full lift down and full lift up trajectories, respectively, with a lift to drag ratio assumed of 0.25. On the x-axis, we vary entry flight path angle, and on the y-axis, we vary ballistic coefficient, which is defined here as the ratio of mass to drag area. Now, looking, for example, at this bottom chart, the farthest left are the steepest entry trajectories, and these result in valid probe trajectories because they intersect the surface of the planet. Moving right, we cross this black line, and in between these black and purple lines are the valid Aerocapture trajectories because these skip back out of the atmosphere but have reduced their energy sufficiently to result in elliptical orbits. And even further right, on the other side of this purple line, we have trajectories that also skip out of the atmosphere but still have sufficient energy to follow hyperbolic orbits. And so for that reason, this region is not valid for Aerocapture or probe trajectories. Now we can consider feasibility for this co-delivery method by looking at these charts. So because we vary entry flight path angle on the x-axis, we want to look along vertical lines. By definition, this concept is feasible when two different ballistic coefficients and potentially also different control approaches, meaning ballistic versus full lift up, provide orbiter and probe trajectories along the same entry flight path angle. You can also look at an entry corridor. So here I've assumed plus or minus 0.25 degrees, and that is represented by these dashed lines on either side of the nominal entry flight path angle. So for the concept to be feasible, including accommodation for the entry flight path angle uncertainty, it must be feasible along all three of these vertical lines, not just the center line. We can also assess other constraints using this chart. So we've contoured a number of other parameters, including apoapsis altitude, peak G load, peak heat rate, and peak heat load, or excuse me, total heat load. for all of these trajectories. So as an example, let's enforce that the orbiter requires an initial apoapsis altitude of at least 300 kilometers. Also, for an example, we can assume that the probe cannot exceed a peak heat rate of 50 watts per centimeter squared. So those are represented by this green and this red line respectively. And then we can look at the region of feasibility. So we've constrained it to the point that it's this gray shaded region is the region of feasibility for this scenario under these assumed constraints. And that results in constraints on ballistic coefficients. So we've ended up with a lift up orbiter that requires a ballistic coefficient of at least 130 kilograms per meter squared, and a ballistic probe that requires a ballistic coefficient of no greater than 100 kilograms per meter squared. So this is to show that the concept is feasible, and I've walked through this example to also illustrate how a mission designer or a reader can impose their own constraints on this chart and get out the resulting constraints on ballistic coefficient and control authority. Now, this feasibility assessment was conducted using bounding cases, using full lift up, full lift down. Of course, for an actual Aerocapture mission, in general, you would want some kind of closed loop guidance to allow the vehicle to mitigate the inherent uncertainties in the problem. And that's often desirable for probes as well to target a specific landing location. So let's choose a point design that meets the constraints that we just identified, and then implement guidance that has been well studied in the literature, and look at its performance and make sure that it actually is feasible, even when we go a little bit deeper than just looking at the bounding cases. So we have an orbiter that can use a lift to drag ratio of 0.25 and has a ballistic coefficient of 130, a probe that has the same lift to drag ratio, ballistic coefficient of 35. Both of these will use closed loop bank angle modulation for their guidance. And thirdly, we include a passive ballistic probe with the same ballistic coefficient as the other probe for the purposes of comparison. And like before, we're at Mars, 6 kilometers per second, nominal entry, flight path angle of -12 degrees. There's a lot of numbers on this chart, but the two main takeaways are, number one, that the guidance performs well as expected based on the existing results in literature, and is able to guide the orbiter and the guided probe to their final states within reasonable error statistics. The other main takeaway is that we can compare the performance of the passive and guided probes, and you could use that to then evaluate, given your mission requirements, is it necessary to include guidance for the probe? So in this instance, I'm showing the histograms for range targeting error, and this is at 15 kilometers altitude, so it's sort of a stand-in for a parachute deploy stage, and I'm comparing it between the guided probe and passive probe. You can see that the passive probe performs about an order of magnitude worse than the guided probe. You'd certainly expect that it would be worse, but plus or minus 50 kilometers range targeting error, not necessarily too large for certain mission applications. So it's possible that depending on your mission requirements, that may be sufficient. So you can use this sort of study to compare whether or not guidance is actually required for your application. So now we'll continue getting more specific and look at an example mission scenario that we've constructed that would take advantage of this co-delivery concept. And so for that, we'll use the same point design as before, selecting a passive ballistic probe. So this is an MSL class orbiter using bank angle modulation, and a shield-like rough lander, where shield is a concept under development at JPL for a very simplified lander design that would forego parachutes or retropropulsion and simply rely on crushable material to land and protect its payloads, which can accept these relatively high G loads. Let's land more than one of these. Let's land 4 or more landers to form a network that can conduct unique science on the Martian surface using this network of small landers. This is in part motivated by an ongoing Keck Institute study revolutionizing access to the Mars surface. And you can see Dr. Zach Putnam's presentation earlier at this year's IPPW, which gave a great overview of that ongoing study. So on this chart, the circles and squares correspond to separation along the along track and cross track directions, respectively. And this is showing that even though the concept I described earlier as having identical entry state for the probe and orbiter, of course they have to separate at some point, by some amount, to avoid recontact in the atmosphere and to spread the probes out on the Martian surface. So we can vary the timing and magnitude of that separation maneuver and look at the landed geometry that results. And so that's what we're doing here, varying on the left, varying the separation timing, and on the right, varying the separation magnitude. The key takeaway here is that for our nominal separation 1 day before entry, with a magnitude of 10 centimeters per second, we can achieve relative separations of the probes ranging from 10 to 160 kilometers on the surface, and we can achieve a variety of separation distances and geometries with fairly small maneuvers performed shortly before entry. So we can still take advantage of this co-delivery technique and then just perform this very small separation shortly before entry. This chart shows the same data as I showed previously, but in perspective. So it is to scale against the Martian surface with equal axes. And to make a fairly apples to oranges comparison, Curiosity drove a little more than 20 kilometers in its first 7 years of operation. The yellow line that I've drawn here across the crater is roughly double that distance, so a little less than 45 kilometers, whereas the width of this image is about 1,000 kilometers, and we span most of it with this network. So the takeaway here being, number one, showing the previous data in context, and number two, being that you could potentially take simultaneous measurements from very far apart on the Martian surface to conduct unique science that would never be possible with a rover, at least not taking that sort of measurement. So to conclude, we've introduced the proposed co-delivery method and shown that it is feasible, and there are results available in the full paper for other planetary destinations. We applied existing guidance schemes and examined their performance compared to a passive probe. Noted that an MSL-class orbiter and a Shield-class rough lander make a nice combination and may provide a path to low-cost delivery of a network of small landers on the Martian surface. And that would be one implementation of this more general co-delivery method that we presented. So to conclude, I'll note that I have an image taken by Marco on the left here, and a GIF of Ingenuity on the Martian surface on the right. These are both very exciting missions performed by small ride-along craft at Mars. So let's think out of the box about the future of small spacecraft at Mars. Thank you. Get it to stop recording.